assistant professor at Occidental College. His parents live here, what, half the year, I think you said, roughly, something like that. So, and it's a story you've heard many times before. He was inspired by seeing the Tetons. So, you know, hence that's probably at least a little bit of a motivation on his work, though there's some great science as well. So Darren Larsen is going to talk to us in a little more depth and a little bit more about some of the technical details of the work that you've had underway for, what, 4 or 5 years now?
Yeah, 5 years.
So join me in welcoming Darren Larsen, please. Thank you. All yours.
Thanks, John. Is this a good spot to stand for everyone?
It's fine.
Yeah, this is great to be here. Last night was fantastic, but it's nice to kind of break it down into a smaller venue, a little bit more intimate. How many of you folks, I see a lot of familiar faces, how many of you were not at last night's talk? Okay, so we're about half and half. So that's sort of what I was assuming. So I figured I would structure the talk kind of a similar way as last night to bring everyone up to speed and then get into some other aspects of the work that we've been doing up here in the national park. So as John mentioned, I'm an assistant professor at Occidental College in LA. But before that, I was in Pittsburgh in New York doing a postdoc there. And before that, conducting my graduate research at the University of Colorado, so just down the road, and at the University of Iceland. I actually have this PhDs from both institutions. It's a long story, but while I was at CU in Boulder, I initiated this project here in the Tetons, really as a means to allow me to spend more time in this fantastic region. I had, as John mentioned, I moved out here for a few years right after college. Perhaps like some of you or like folks you know, just almost magnetically attracted to the Tetons. I kind of flocked out here, and then I thought actually I was working for the Teton Science School here in town as an environmental educator, and I thought I was going to graduate school for just a brief 2 years to get a master's, and then I'd be right back because this is one of my happy places. I feel like my heart center is here. But as you all know, the path you think is going to lead you right back to where you're expecting sometimes took right off. So that was in 2007 that I left here thinking I'd be back in 2 years with a master's to resume my environmental education, and now we're something like 11 years later. I live in Southern California, but I get to come to the Tetons frequently for research, so kind of mixing my vocation with my avocation. I wanted to thank all these collaborators. Many of the folks whose names are on the screen are locals, actually, and have just helped in the field for a day or repeatedly for lake coring or other types of field work. Others are students and collaborators or national park personnel. So, of course, research like this is really not done independently. It is a very collaborative type of work. And then also the funding for this research, which was initially started back in my graduate school days through seed money provided by the National Park Service and the Grand Teton Association. So some of these grants and fellowships, which you may have heard of or be aware of, are actually terrific for initiating projects that can then expand into a much larger scope. So I'd like to thank those folks. A little about me professionally. I'm a quaternary geologist and sedimentologist, so much of what I do involves targeting sedimentary deposits relatively close to the Earth's surface or on the Earth's surface, and using those deposits to study some aspect of surface processes, whether they're related to climate or environmental change or tectonic activity. So in a sense, I kind of wear many hats. I could classify myself as a sedimentologist, but also as a paleoclimatologist or hydrologist, and also a geomorphologist. And so this involves a very interdisciplinary type of research. It also involves being out in the field to actually collect these sediments. So I'm very much a field geologist, and I'll show you in a moment all the places where I've worked to study some aspect of surface processes and Earth's climate or environmental systems. The fun part is being out in the field, like here in the Tetons. Maybe the less fun part is being in the lab and processing this data, which can, of course, be tedious, but is the necessary evil for producing these data sets. So these are places that I've worked. I've just kind of listed the common themes here. We'll be traveling, of course, to the Tetons here in the western US, where this project spans everything from paleoseismology, which I spoke mostly on last night and which I'll touch on again today, but also glacier geology and climate change, or perhaps environmental change along an elevation gradient of the Tetons and in these regions that are public lands where we know we're living in a time of change, and how the changes in temperature or water availability are going to affect these beloved places like the national parks or the Grand Tetons is something I think we're all interested in, right? We have a stake in this game. So to place context for this talk, I just put a few bullet points up here saying that both climate, like I was just alluding to, but also tectonic processes can really influence mountain landscape evolution and the geomorphic development of these landscapes. Alpine ecosystems, similar to maybe Arctic ecosystems, are particularly fragile. So these mountain landscapes, which we live right at the base of here in the town of Jackson, are sensitive to disturbances, whether it's related to abrupt climate change or to tectonic events like earthquakes. And so, or importantly, actually, human activity, of course, right? So much more recently, the impacts of this growing human population is stressing our natural resources, of course, and can cause disturbances to these sensitive ecosystems. So these disturbances pose very serious threats. So in the case of earthquakes, right, these are very practical, relevant threats to the way we operate or the way we live our lives here. Maybe some of them are more indirect. Those related to changing vegetation in response to changing climate might not be something we immediately see or feel, but something that we kind of more perceive over longer periods of time. And so those pose serious challenges for the way humans are adapting to change, and also for resource conservation efforts in places that are, again, conserved here in the national park systems. I'm going to try and convince you today or demonstrate that the Teton Range presents a really exceptional opportunity for this type of work. It's not solely that I wanted to spend my time here because I love it so much, but I also believe that this is a veritable natural laboratory to evaluate surface processes, deep earth processes, and how those two things interact with each other. And then, of course, the national park contains a pristine and minimally impacted ecosystem that hasn't been altered by human activity. So it's a terrific place to conduct research of this manner. And for those reasons, really, folks have been conducting scientific research in this region for almost a century now, for quite a long time. And so I've listed a bunch of studies that have focused on the tectonic, geomorphologic, glacier geologic, and ecologic aspects of the Grand Teton and Yellowstone region or ecosystem. And so some of these earlier studies were done back in the 30s when folks were kind of just starting to come out here and start posing questions, scientific questions that they thought could be answered by studying this landscape. However, despite all of this work, and this is something I realized after reading through these papers about 8 years ago now, I began to realize that there were still some questions, and of course that's why science is so interesting to myself and to, of course, many of you, is that there's always more to learn. And so the more we know, the more we realize we don't know. And these questions related to the post-glacial climate and tectonic activity of the Tetons, I think are still outstanding and are what really attracted me to conduct work in this region. So the goal of this project is really to study two different related but somewhat independent topics. The first is climate-driven changes and disturbances and how those have operated in the Teton landscape in the past and how they might change or evolve leading into the future. And the second here is to understand how tectonic activity has disturbed or interacted with the landscape. The way I'm going to answer these questions is using sedimentary archives, and in particular sedimentary archives that are contained in lakes along the range front at various elevations. So this is just a Google Earth image here of the Teton Range, where we're looking kind of down onto the eastern front of the mountains. This is Jenny Lake in the center here, and Phelps Lake to the south. And so all of these yellow dots here are places where we've extracted sediment cores, and I'll explain how we do that later in this talk. And then analyze those sediments to try and answer some of these questions or study these topics here. Now, I realize that I am moving somewhat quickly because many of us have seen this before. If I'm moving too fast for folks, just let me know to slow down.
Okay. The blue line is what? The drainage?
Yeah, exactly. So here we are looking.
Darren, will
at
you
the
try
mountains.
and do that? Keep talking. I'm going to see if I think I can brighten the screen up.
Oh, okay.
Good.
I just need to get to the right spot, which
So I've drawn two lines on this image.
Yeah, it looks like
the first one is a black line right along
it's
the range
already
front,
100%.
and that's the trace of the Teton Fault as it runs along the mountain
Can you
front there.
change the picture mode, John,
Well, that's.
to like a high def?
Let's try this real quick first. See what that does.
Ooh, much better. What you
Okay.
did is good.
Okay. So I just have to figure out how to get out of this.
There should be an exit button somewhere.
Well, yeah, out of these 50
How about
buttons.
the little arrow that you can continue down?
I don't know if I want to go down. So let's see. Sorry.
No problem.
Is there a back button or menu?
There should be an escape exit. There we go.
Bingo.
Sorry. That's
The
much
black
better.
line is the fault, and then the blue line is
Drainage.
The drainage divide, and so this is quite
the
interesting.
divide, the top.
Well, that's
No.
what's interesting is that it's not actually the crest of the range, it's the drainage divide. So it's the watershed divide, meaning all snow or rainfall, precipitation that falls on this region, if it falls above that line, or in this case to the west of that line, it will drain out into Idaho, and if it falls to the east, or on the front side here, it'll drain down into the valley of Jackson Hole. So that's the watershed divide. What's interesting and what's unusual in the context of many mountain ranges around the world is that the drainage divide is not running right along the crest of the mountains. And so that has caught the attention of folks, and that speaks to how the range has been uplifted and then also incised by glacial activity. And so the drainage divide is actually being pushed westward, whereas the crest of the range is actually standing proud to the east of that divide. And that has interesting implications for kind of the tectonic history of the range itself.
Is the blue line about as far west as the glaciers got?
Yes, and so that blue line is basically the heads of the cirques of some of your favorite canyons here. So in this case, this is at the head of the North Fork, Middle Fork, and South Fork of Cascade Canyon, and then it's running just to the west of the summits of the Grand Teton and Middle Teton and South Teton there on the other side of what I believe is Alaska Basin, maybe?
Yep.
Or I don't know if that's, but near the Schoolroom Glacier at the pass at the head of Avalanche Canyon, where Avalanche Canyon kind of meets the South Fork of Cascade Canyon here. It's hard to, it was a difficult line to draw because of our perspective. We're not looking in map view. But this is interesting, and I'd be happy to talk with you more about this or direct you to some papers where folks have studied this relationship between the crest of the range and the watershed divide.
You said that it's being pushed. Is it being pushed by earthquakes or by tectonic plates or what?
It's being pushed by the way the mountains are uplifting, but then also the way they're being carved out by glacial activity. And so these cirques have been excavated by originally river incision, but then more recently periodic occupation by Alpine Glaciers, so during ice ages. And these glaciers are very effective agents of erosion, and so there's headward or greater erosion happening at the cirque head wall, and so it kind of eats back up into, just the same way a waterfall might migrate upstream. The glaciers are eroding headward up into these canyons, so the canyons are being pushed further westward. And with it, they could either be capturing other drainages or continuing to push that drainage divide as the cirques themselves travel west. Okay, so I was going to just first talk about some evidence we have for climate change here in the Tetons, and then about these tectonic activity that's happened. In both cases, because since we're talking about glacial activity, we're using sediments contained in these lakes, which we know were effectively, these bodies of water are occupying basins or depressions that were excavated by glaciers in the past. In this case, the most recent glaciers that occupied the range. And so they were only uncovered at the end, beginning at the end of the last ice age. So these sedimentary archives here are not that old, right? They only date back to the time of deglaciation, which we're still kind of refining our age of. So in both cases, I'll be studying basically the last 15 or 14,000 years of time. So that's a relatively short amount of time with respect to the age of the mountains themselves, right? So we're just looking at the past roughly 15,000 years in this study. I'm going to place this in a longer term context though, using data produced by some previous studies and ongoing studies here in the range. So this is a very similar map here. This might be more helpful to put this idea of a drainage divide and the crest divide in a better perspective. We're looking now in a somewhat similar direction, but it's an oblique aerial or satellite image. This is the Landsat satellites, and this is the Valley of Jackson and the Teton Valley to the west. You can see that there are canyons being incised into both sides of the mountain range. So there's glaciers flowing out into the east, like we're familiar with here, that have carved these glacial lakes, but there were also glaciers that were occupying the range that were on the other side of the drainage divide and flowed westward into Teton Valley. For various reasons, those didn't create these broad lobate terminal moraines that now impound the lakes that constitute some of the major highlights of Grand Teton National Park. These glaciers instead ran out into the valley and didn't create large moraines that would have then dammed meltwater, creating these lake basins. So it's kind of interesting to compare them. The gradients of the valleys are very different, and the bedrock in which they're incising through is also different. So there's differences along the east and west side of the range, which may account for these differences in glacier geomorphology. I'm not sure I want to say anything more about that. We had some interesting discussions at the end of, or during the talk yesterday and at the end of the talk, so I've kind of inserted some things that could be relevant as we go through today's talk and discussion, and I just wanted to have up here so we could flip back to them. This is a geologic map now of the region. Many of you have probably seen this before. It's just a fantastic map showing the bedrock and surface geology that is expressed in the range. And so here we're looking at kind of the heart of Grand Teton National Park. This is Jackson Lake for reference here. I know it's probably difficult, you certainly can't read any of these, but you can kind of get a sense for differences in color here. For the most part, the mountain range, I'll flip back here, the highest peaks are composed of a crystalline core, so a quite old, very old igneous and metamorphic core of the range that's mantled or draped by westward tilting Paleozoic strata, sedimentary units, shallow marine sedimentary units for the most part, and in some cases some volcanics as you get further up into the range. So we have this crystalline core of high peaks, and then these pinks, or purples rather, that are on the western side. Those are those younger Paleozoic rocks. The valley itself is almost all yellow, or some hint of yellow. That's basically sediments, right? So we have bedrock forming the mountains, but then the valleys is a basin, and so that's collecting sediments. Most of these sediments were deposited in the relatively recent past by glacial and fluvial deposition. John and I actually had, and Mike had an interesting discussion about Signal Mountain, and so I've included some slides on that also. And so for reference, this is Signal Mountain here, and there's some interesting outcrops on Signal Mountain, which are quite subtle, except that they hold really, they hold some of the most compelling evidence for the timing of uplift and initiation of the Teton Fault. So, and it's really a fascinating story. So I thought I would show some slides on that because it's one of these classic examples of how relatively subdued geology, or something that most people wouldn't even stop to look at, can hold really really great clues and evidence for these major processes. And it's been interesting, the development of thought on this matter which is important for understanding the activity of the fault. And of course, it's important to know when the fault initiated or when the onset of faulting began. So a simple question like that actually turns out to be quite difficult to answer. So here's a map of the western U.S. to put us even in a more broad scale here, and I've put a bounding box around the Yellowstone, northwestern Wyoming region. Of course, the Tetons are kind of smack in the middle of that. But it's helpful to see where we are located geomorphologically or geologically within the western U.S. We're in the Middle Rocky Mountain physiographic province, but we're right on the eastern edge of the Basin and Range province, which of course must be familiar to many of you. I'm sure some of you have driven through the Basin and Range, and this region is characterized by extensional forces that are effectively pulling the crust apart, causing these roughly parallel mountains that are separated by these valleys that are basically falling out from under their feet. So I like to tell my students in Geology 101 when we talk about the Basin and Range, the width of Nevada, and I don't have the states here clearly marked, but Nevada is basically this. The width of Nevada has effectively doubled due to extension during basically the last 15 or 16 million years. So we're right along the boundary of that. As I flew in, again, I live down here in Los Angeles, which I think is just on the map. I flew over the Basin and Range, and as you're flying over this Salt Lake, you can see clearly the Wasatch Fault, which is similar to the Teton normal fault. And you can just follow that scarp right along the range front. And here we are now facing the opposite direction, but we have possibly similar forces acting in this region. What we'll talk about a little bit, though, is how it's not quite as simple as that, because in this case we have this relatively local effect of the Yellowstone hotspot, which the North American plate has been traveling over, and which no doubt has influenced the tectonic dynamics of the Tetons. I also wanted to overlay this map with the extent of Alpine glaciers in the western U.S. during the last glacier interval. And so this is a map put together quite a while ago now, 35 years ago, by Porter et al., showing the extent of these alpine ice masses and also the southern boundary of the ice sheets to the north, the Cordilleran and Laurentide ice sheets. But as you can see here, so this again is the Yellowstone Grand Teton region. This region harbored the largest ice mass outside of the great ice sheets during the Pleistocene, as well as some other mountain ranges you may be familiar with. This is the Sierra Nevadas here, which had glacial ice, the Cascades. Here's the Uintas, the Front Range of Colorado, and then many of the smaller ranges in Idaho and into Montana. To zoom in on that, because this kind of came up in yesterday's talk, where the boundaries of these ice masses were. This is, again, pretty broad scale, but folks have more recently, I guess in an effort primarily led by Ken Pierce and others at the USGS, have really tried to identify the limits of these ice masses in this region. And so I thought I would put up a few pictures that zoom in more on this Yellowstone Jackson Hole region here. This is in a paper that I can send to you that's freely available for download, published by the USGS just earlier this year. So it's quite exciting, and it's really kind of a life's work of the authors.
Is that Pierce's new?
Yeah.
This is brand new.
1835.
Yeah, professional paper, 1835. And I have a copy if anyone is interested. It is great, and it really covers a lot of the surface geology of this region. So now we're zoomed in on the Yellowstone Plateau, which is in the center frame here, and to the south, of course, the Teton Range. And it's showing, it might be difficult to see from where you're sitting, but it's showing the ice extents during the last glacial maximum, which we refer to as the Pinedale Glacial or Pinedale stage, which actually had multiple pulses within it. And then in pink or salmon colored here is the ice extent during the penultimate glacial. And so the Pinedale culminated, we can just say something around 22,000 years ago, 25 to 22,000 years ago, whereas the Bull Lake culminated around 150 to 140,000 years ago, roughly. And so those are very rough ages. They put some of the ages, I believe, on this map here. So they're showing ages in the realm of 19.8 or 20, 18, 17, and they're showing the places where they dated the extent of this ice sheet or Alpine Valley glaciers during these different glaciations. So this really demonstrates that almost all of Yellowstone was covered, the Teton Range was covered by these valley glaciers, but the valley of Jackson Hole was not covered, and this is just, I'm showing now just figures from this paper. So now we're zoomed in right along the Teton Range. This solid black line here is showing the limits, the southern limits of that Yellowstone ice cap as it advanced south into the valley of Jackson Hole during the Pinedale times. And so you can see it covered all of Lee Lake and Jackson Lake. It stopped just short of Jenny Lake, and then had another lobe that extended a little further south, but for the most part didn't get too far down into the valley. In contrast, the red line is showing the advance of the penultimate Bull Lake glaciers that advanced right through the valley, terminated down by Munger Mountain to the south of us here. So quite a big difference in the extent of these two advances. There was some questions as to whether where this ice boundary was because it relates to the fault activity and to the timing of deglaciation of the mountain range here.
Question. What relative time periods were the two glaciations?
Yeah, so
Sorry.
let's see, did they put their ages on this here?
Relative.
You said it already, 15,000 years ago and 135, 150.
Yeah.
So, and which one was which?
The Pinedale was the 130 something.
No, it's the other way
So
around.
he said opposite.
Bull Lake is the old one.
Bull Lake is the older one and the
That's
bigger
old
one.
Thank you. I'm
Yep. And then this
here,
is
I
the
don't
younger
have it
one.
down.
Yeah, no problem. It is, when you flip through, I suggest you read through this if you're interested, because there is so much information here. And as you dive into it, you realize that it's not even this simple. Within the Pinedale itself, there's evidence for multiple kind of advances and retreats of the ice sheet on these kind of multi-thousand-year time scales. And so this is really just showing the kind of broad Pinedale limit. There's these three known phases of the Pinedale, which were all kind of culminated in this broad region, but this is, I believe, they're just kind of showing the maximum extent at any time during this Pinedale episode.
You might let everybody know that this is just the end of 2.5 million years of...
Right. So these are just the last two ice ages, and by all accounts, there's probably something like 20 or 22 ice ages that have occurred in this region based on evidence that we have from outside of this area, from marine sediment cores and ice cores and things like that. So we know that for the last 2.5 million years, this 2.56 million years or something like that, the Earth has experienced periodic glacial and interglacial episodes that are largely in response to the way we are orbiting our star. So the mechanics of our orbit around the star, the way our position in space and the distance from the sun, for example, can influence climate in such a way that we've been experiencing these relatively long glacial episodes, something like 80,000 years long, or up to 100,000 years long, that are interrupted by these brief interglacials that we're, of course, used to today. This is an interglacial, and those interglacials really only last 10 or 15,000 years, so it's a brief window of time. Much of the last 2.5 million years, the planet has seen these large ice sheets and growth of ice masses in the northern hemisphere in particular, particularly at high latitudes, or high elevations and high latitudes.
So when you said the Tetons were covered by ice, do you mean the valley, the Alpine valleys are filled, or the Grand was completely covered by ice?
That's a good question. It's unlikely that the very summit of the Grand, for example, was covered by an ice sheet. That was probably some sort of nunatak that poked out through these connected Alpine glaciers, which may have formed kind of a linear ice cap in a sense that was probably punctuated by the highest summits, which simply are too steep. The slopes are too steep to really harbor much ice, and they're tall enough to pop through that. But during the Bull Lake, it's unclear. I'm not sure if they refer to that in this paper, but that's an interesting question.
There's earlier paper by Pierce et al. And they have, for the Bull Lake, 150,000 years ago, they have good estimates of the elevation of the ice surface in Jackson Hole. At this point right here, it's 1,500 feet of ice. At the airport, it was right at 2,500 feet of ice. And by the time you get up to Jackson Lake, you're around 3,000.
Wow.
So most of the, half the mountain range is sticking out.
Yeah.
Right, so up to 10,000 feet roughly would be ice, and
Close.
above 10,000 would be ice-free
9,000.
at the northern part.
Yeah.
So yeah, again, these are just the last two glacial episodes. We're going to be focusing much of this work within the time period of the end of the last ice age. So this Pinedale phase here. So this is the glacier extents during these two ice ages, and what the authors begin to realize is that the dynamics of the Yellowstone hotspot influence the elevations of the area, because in front of this, you can imagine the hotspot almost as like a ship plowing through water, creating this forebulge in front of it, which creates these high elevations in the foreground here of Yellowstone, and kind of poofs the land up, but then also creates this low elevation plain, which has a way of funneling atmospheric systems up into the Yellowstone region, creating high precipitation rates on these higher elevations and along this trough here. So the authors suggest that this increased precipitation is largely what is responsible for creating these large ice masses. And it's also the migration of this hotspot, which they place some ages on here, which they think is responsible for initiating what could have been pre-existing faults in the area and the onset of the Teton Fault.
Are the black on that, the heavy black lines, the faults?
Look like it.
They look like
Yeah,
it.
these are major Holocene faults.
Okay, good.
But then they have other faults along here. But yeah, those are mapped fault lines there.
Okay.
I think those are the major Basin and Range faults.
Yep.
Holocene.
Yep.
Right. And then to just show you a few more pictures from this paper, because I really think it ties into what we're talking about, and we were having a fun conversation about this last night. These are some data sets that I had sort of forgot about. These have been known for a long time, really, but it hasn't been, I think, as clearly laid out as it has now just this year. So again, this is looking at looking south at the north end of Signal Mountain, looking at some of these outcrops, these two tuff deposits of varying ages here, and then you can also get kind of a sense of it, the varying dips or slopes of those deposits, which in addition to this lacustrine deposit was likely laid down flat and has since been tilted by tectonic activity of the fault. And so what this is demonstrating here is that these two earlier deposits have the same tilt, and it wasn't until this more recent Huckleberry Ridge volcanoclastic deposit around 2 million years ago where we see a difference in the slope, which would suggest that the onset of sloping or tilting or faulting in this region happened soon after this time period, which we can date to around 4 million years, or around that time period. This is quite a young age for the onset of the Teton Fault, and it sort of stands in contrast to ongoing another recent study. So this is one of these kind of classic scientific questions or classic forms of how a controversial question can kind of get progressed in the literature. So now this is a different group using a different tool trying to determine the onset of the fault. In this case, they're looking at minerals contained in these crystalline rocks and using low temperature thermochronology, determining the age or the time at which those minerals cooled in the Earth's crust, which they can use as a proxy for the depth in the crust, because we know if we make some assumptions about the geotherm within the Earth. And so what this group demonstrated here, this is another paper which I can send around that just came out last year, is that they see evidence for cooling much earlier, around 15 to 13 million years ago, which in the northern part of the range, which they're interpreting to mean that the onset of faulting occurred much earlier in that part of the range. And so at face value, these seem to be two contrasting interpretations for the onset of faulting in the range. This is interesting, and I think it's a discussion that is ongoing. As I understand it, John was saying this researcher here, who's at the University of Kentucky, will be speaking
Next summer
at the Geologist of Jackson Hole. So that's really interesting. I'm interested to hear what some of their more recent findings are. So this is kind of fun, right? This is just when there's a problem that has different viewpoints. That's exciting science, I think. Okay, and that sets the background for this study, because much of what we'll be talking about with regards to the tectonic history of the fault is about developing these slip rates over various time periods in the past. And so to put these in a longer term context, of course, we need to know how long the fault has actually been slipping. So that's kind of the baseline for interpreting these more recent results that we're generating through this study. So I think many of you are familiar with this, though. Here's just some of the mechanics of the Teton Fault, which runs along the eastern range front. It's about 60 or 70 kilometers long, although the length of the fault is something that is also being more carefully studied now, and it's thought that it might actually run up into Yellowstone and terminate there, but is kind of obfuscated by the kind of local tectonic activity of the hotspot. Where the southern boundary is also a little bit nebulous, and so
No,
folks
it's not.
What's that?
No, it's not.
Well,
We can talk about that afterwards.
we can talk about that afterwards. But it's considered to be an active fault nonetheless, and this is really due to the surface expression of the fault in these relatively young glacier deposits. And so we know it's been active in the recent past. We know just by standing back and looking at the Tetons, at the shape of these mountains, that it must be an active fault, because these are such sharp, steep mountains. If the pace of faulting was less than the pace of erosion processes, you'd see much more rounded and gradual mountains, right? So we know that faulting must be outpacing erosion and these processes which act to wear down these mountains. So we know there's active faulting. And yet what's interesting is that, and John had this kind of in the prelude to my talk last night on the website, is that we see this in this region a very high active seismic activity over the past 140 years, or since 1871. The Teton Fault itself has not experienced an earthquake. So we see there's earthquakes all around us in the Gros Ventres and north into Yellowstone, but along the Teton Fault itself, we don't have evidence for a historical earthquake. And that's, of course, interesting, right? We want to know when the next earthquake along the fault is going to be, because millions of people visit this park every year. There's a community down here in Jackson. We have dam there's important infrastructure which would be heavily influenced or perhaps compromised by a major earthquake. So that kind of sets the stage here. This is another way of looking at the Teton Range. We're looking now in profile view, looking north at the Tetons, and we can see these two basins that flank the mountain range here, the Teton Basin to the west and the Valley of Jackson Hole Basin to the east. These authors, Foster et al., have placed the approximate location of the Teton Fault along the eastern side and tried to show, I think, fairly effectively in this image, the depth to the pre-Cenozoic basement, so the depth to basement material, showing really how thick the basin of Jackson Hole is due to this normal fault activity. And so the surface expression of the Tetons is not representative of the total slip along the fault, which is much greater than that, 3 or perhaps more times greater than the surface relief that we observe as we're driving up into the park.
The very bottom line is marked flexure, but tell me a little bit more about what that's trying to connote.
So it's trying to demonstrate the mass of sediments that are being moved from this region or from other regions of high elevation into this region here. And so that mass is isostatically depressing the crust.
Okay. So that's kind of a surface in the crust, basically, prior to the sedimentation.
Yeah, and I forget exactly this might be just modeled, or I forget how they're putting that line on there. But I can refer you to this paper also. It's an interesting paper. They're trying to relate the geomorphology of the range to kind of meteorological data, looking at the amount of precipitation that's happening along various catchments, and understand maybe how that has influenced the erosion that's taking place in each of these canyons, where the foci of erosion is, and whether that's due to glacial occupation or actually these interglacial fluvial processes. So it's pretty neat. As I said, there's evidence for recent fault activity on the landscape, and both in the shape of the mountains, this steep, asymmetrical, very jagged shape of the mountains, suggesting rapid uplift, but also along the range front, we see the scarp itself offsetting the surface of the mountains, the surface of the planet, and those surface deposits. As I was showing yesterday, many of the images that I'll show from now on are high-resolution digital elevation models that were produced by kind of a joint effort through the National Park System to map the national park and surrounding lands like the Elk Refuge using LiDAR, which produces very high-resolution raster data sets of the landscape, which can see right through vegetation and really aid in doing some superficial mapping of the park. So
I meant to ask you last time. Is that data set available?
So I was just telling John this. As far as I know, it's available. They, Kathy Melander, who some of you may know, who is now retired, she was the GIS specialist for the park up until I guess the year before last. She gave me this seemingly freely. I believe it's public data. The problem is that it's a huge file. It's like 100 or 200 gigabytes. So I had to physically give her a hard drive, which she spent an afternoon loading the data on, and then I came by later and picked it up. But I think if any one of you wanted it, that would be available. John was asking if we could, we can then kind of manipulate this however we want and make it maybe more manageable by turning it into a KMZ or KML file, which we can then load in Google Earth. And that's something I can work on, and then if I do, I can send it to you guys, and you can disseminate it how you will. Because it's a great data set. And so this is an example of some of the fun you can have, is looking at these features that show up in Google Earth imagery, which of course was kind of revolutionary when Google Earth came about. It's kind of changed the way we do science, really, because now we can really look at the planet from afar, and it is, it's a game changer. LiDAR is much the same way in that we can then do better than this satellite imagery by looking at some of these features which might be covered by vegetation. So like here's a forest right to the south of the dam, a mixed conifer forest, whereas when you can't really see much of the geomorphology here in the forest, but if you look at the LiDAR, you can notice all of these small drainage networks here, these ridges and valleys, perhaps moraine deposits here, all sorts of really neat features that you otherwise would be hard-pressed to notice, even if you were walking around through this. I'm sure all of us have walked through deadfall in a forest, and it's almost impossible with the leaf litter and the trees to see what the surface geomorphology is. So it's terrific. Here's another neat example of Phelps Lake here at the mouth of Death Canyon, of the lake, which is shown in colors here related to the depth of the water in the basin, and then how it's bounded by this moraine system, which is vegetated. As many of you know, if you've hiked along Phelps Lake, there's forests growing along these moraines, and yet here with the LiDAR you can just make out all of these individual parallel ridges, which are multiple nested moraines, showing that how the snout of the glacier was fluctuating prior to its eventual retreat up valley. So there's all sorts of neat features there. You can see evidence for landsliding and debris flows, and then also the Teton Fault shown here that you can pretty clearly pick out as it runs right along the range front. Some interesting stepovers in places.
The, at the front of the lake, it almost looks like, it could be lake sediment, I don't know, but it looks like there's 3 or 4 terminal moraines. And you wonder if you're seeing a number of the valley glaciers. You know, I'm just kind of curious just looking at that image.
Almost all of the lakes, all the terminal moraine systems have this really well-preserved nested complex that has multiple crests that are nested inside of each other. And I think I have some pictures of it a
For
little bit
Jenny,
later on.
you do, yeah, for Jenny.
For Jenny Lake, folks, Ken Pierce and Joe Latard and others have tried to date these features directly using exposure ages on boulders resting on these individual moraine crests. And it seems that there indeed is a kind of time transgression with the older moraines being most distal and getting younger up valley, which
Are
you'd
they all
expect.
within, like,
They're all the last Pinedale.
Okay.
Mhm.
They have to be.
The lake itself only corresponds to the timing of the last pulse of glaciation. And so the lake was formed perhaps multiple times, but if it was formed if the glacier uncovered the lake multiple times and ran over it again, the sediments in the bottom of the lake, and I'll talk more about this in a second, only correspond to the timing of the most recent or the very last retreat, because every successive kind of ebb and flow of the glacier would have censored any or bulldozed any sediments that were deposited in the intervening time when it had receded and then advanced again and receded. So it's only the lake sediments have only been continuously deposited since the most recent or the very last phase of glaciation.
Can you show on the blow-up picture where the fault trace is? It's easier to see on the other
Right,
one.
so I've changed the hill shade here, and I actually changed the sun angle to bring out some of these other features that I was interested in here. So you can play with the sun angle to highlight different faces, or aspects, I should say, of the morphology. I changed that a little bit here so it's harder to see, but this is the fault scarp here that runs right along. It almost looks like a ridge.
So this is a blow up of a piece of the other lake?
Exactly. So
Okay,
this.
so what piece? Where?
Right at the very upper part.
Yeah, so it's basically this.
Right there,
bit
right at the
here.
top.
You can point out that right angle and that offset in the
So
fault.
yep, this step in the fault
It's
here.
black
Yeah.
on the other one.
Wow.
Yeah.
Yeah, you
Yes.
can see
Yeah,
that.
you can see it.
Holy smokes.
And you can see the summer trail in here, which many of you I'm sure have hiked down.
Mhm.
The trail goes
Oh, yeah.
right along the fault. So you can see it here. There's the big switchback, and then the last switchback that takes you right up onto the moraine crest goes right through the fault scarp. And if you're paying attention, you'll see that as you're hiking that last little bit of the trail.
I was looking at the part, thinking of the fault as you come further south. It's the black line, right?
Yep. So
That-
and you kind of
it's-
lose it.
It's interesting. I
And then it
can't
steps
really,
in here.
From here I can't see the trail, but it's damn close to where the trail goes once you come further south, heading towards the village.
Mm-hmm. Yeah, you kind of lose the trail here, somewhere up in here. I haven't actually hiked that in some time now, but I have gone down this one to look at the fault scarp, and sure enough, that viewpoint right at the crest of the moraine there, where you look at that beautiful view down onto the lake, is basically right there on the scarp itself.
And it looks like one of the switchbacks touches it as well.
Touches it again, yeah, the very last one.
And so is that a little landslide, or is that just the edge of the moraine?
This here?
Yeah, where it sort of.
It looks like it's scalloped out, but I actually think it's a ridge here, like maybe a debris, a fan of some kind, within the backslope of the moraine. You can spend an entire day
Just looking at that
flying
image.
around and looking at just this picture, but then imagine the whole park. It's worth trying to get this data set to you guys because I think it's
Yeah, we
it's
could
terrific.
probably have some fun with that.
Yeah. Okay. Where am I here? So, again, I'm going to be focusing on the timing of deglaciation, which is really the last 15 or 14,000 years ago, and I'll be providing some evidence that helps us understand when the timing of that deglaciation was of these alpine glaciers that occupied the canyons along the range front. And so this ice retreat has been documented by the timing of moraine abandonment and also by the basal ages of the lake sediments contained in the lakes. many of these glacial features contain evidence for faulting that's happened since that time. And so here's another aerial view showing the LiDAR of the mouths of these three canyons here, Avalanche Canyon, Garnet Canyon, and Glacier Gulch. And you can see the Teton Fault cutting right across these Pinedale age glacier deposits. And the idea is that these glacier deposits are being constructed over periods of thousands of years, and once they're abandoned, as the glaciers retreat, they are no longer being kind of rebuilt up, and any faulting that occurs or offset that occurs will then be forever preserved, essentially on those landscapes. And so we can go around and measure the height of the offset or the displacement along the fault, and say something about the amount of displacement that's occurred since those moraines were in place. So it's this neat combination of developing these glacier chronologies with fault mapping. And so we can say, okay, if we date these features to around 14,000 years ago, and then we measure the amount of offset, we can come up with average slip rates over that time, which when we do are quite high. An average of 2 millimeters per year of slip occurs along the fault. So that's substantial, and of course that's not happening gradually. That's instead happening through a series of very catastrophic earthquakes as the fault displaces or ruptures along either the entire length of the fault or along subcomponents or segments of the fault. And so it's this amount of displacement occurred through a series of earthquakes, and much of what this work is trying to do is determine what the timing and frequency of those earthquakes was over the last 14,000 years. Okay, the evidence we have for faulting during this time period is actually quite scant. It's faults earthquakes are relatively destructive events, and then these alpine regions are also not exactly constructive landforms, and so there isn't very much sedimentary evidence for the timing of past earthquakes. One of the ways in which we determine the periodicity of past earthquakes or paleoseismic techniques is through trenching of faults. And so this is how we know, for example, when the last few earthquakes along the San Andreas Fault were, along the Wasatch Fault, and that has been done here only just once along the Teton Fault, largely due to the logistical challenge of digging a trench across the Teton Fault, which is maybe not at the top of the mountains, but in the mountains nonetheless. There aren't very many roads you can access to bring in the equipment that it would take to excavate a large trench across the fault. So that has been done, and twice now, in a major way. Once was back in the late 80s in Granite Creek at the mouth of Granite Canyon, and then once just this last September, some of you may have recalled reading about or visiting the trench that the USGS excavated at the Teton Village Ski Resort. Just above, I guess that's the Union Pass lift there on the skier's right or looker's left part of the mountain. They excavated a large trench there to try and replicate this study along a different region of the fault. And so the idea of trenching a fault is that you dig a trench perpendicular to the fault scarp, and then you're looking for features that have been offset through previous earthquakes. And then if you can somehow find a way to date the age of those features, you can date the timing of a past rupture event and the total displacement that occurred in that individual event.
Pierce commented that there's supposed to be another trench dug, a hand dug trench, again later this year, I think.
That's Glenn Thackeray's work.
Yeah, so I am collaborating very closely with folks who are digging trenches in multiple locations along the fault, but not these large trenches. Instead, they're digging hand trenches, if you can believe it. It involves essentially an army of students and strongbacks to dig these trenches. I have pictures on my computer. I can show you what these hand trenches look like. I joined some of their field operations last year and the year before. In many cases, they're with just hand tools or moving boulders that are the size of this TV. So it's not as simple as just kind of digging a trench in the sand or in mud. These are very large clasts, very high energy deposits that have boulders in them, and that's sort of conveyed here by this picture contained in John Bird's thesis. So this was part of a PhD thesis at the University of Utah, where they trenched the fault at Granite Canyon, and they found charcoal remains from burned organic material contained in a paleosol, or an ancient soil layer that had been offset. And they dated those remains and came up with an age of roughly 8,000 years ago for the timing of offset of that fault. Then things get a little tricky, because then you begin to read various interpretations of the fault itself by the folks who were there, and they begin to kind of change their mind as to whether there was one event or perhaps two events that caused the total amount of displacement of that soil horizon, which they measured to be around 4 meters. And so when you read these things, it's actually very confusing. And I've spoken with Bob Smith about this, and I'm sure maybe he's talked about it with many of you. It's unclear, really, and so then they've backfilled this trench, so it no longer exists. They have pictures of it and everything, but it's not as if we can all just take a field trip to this trench and look at the stratigraphy and try and piece it apart. So we kind of have to just go off of the recollections and the data that the folks who were there generated. And it, to me, seems a little unclear whether or not it was one event that happened 8,000 years ago, or perhaps two events, with the older being 8,000 years ago and a younger event at 5,500 years ago.
When Bob cites it, he always cites two events.
So that's true, but when you actually, yes.
That's just what he says.
But then when you read the manuscripts, they say one. Like I would imagine that the PhD student who was in the trenches, so to speak, really had his nose to the outcrop, and in his thesis he seems to lean towards there being one event. So it seems that they were even amongst the
John used to work for me, and we talked about it.
Okay.
You're spot on. He and Smith had a bit of a disagreement.
Yeah. So hopefully this new trench put in at the ski resort, which isn't far from the Granite Creek Trench, really, might shed some light into that. I was at that trench in September. I was in the trench, and there was an army of people in there who had, many of whom had a lot of experience with fault trenching along the Wasatch and San Andreas, Southern California faults. And they're pointing out these colluvial wedges and common surfaces that have been offset, and it's very difficult. If you're not familiar, if you don't have experience being in these trenches and looking at the stratigraphy, it is confusing. Even the way that the light will change along the trench wall over the course of a day, you think you have it figured out, and you're drawing these, what you think the stratigraphy is, and then the shadows change a little bit, and it looks completely different, or it begins to dry out over the course of a day or 2 days or a week. So it's subtle, and I leave that to the experts. But they seem to think that they captured two recent events, the oldest of which they think is quite old, or I'm sorry, the youngest of which they think is actually quite old, in the 8,000 year range. So
have you seen any of the papers come out yet?
That's probably not going to come out for a while, because it's the USGS, and it's that they just trenched it in September.
Okay.
The data from Thackeray and Zellman and their group along these hand trenches up by Lee Lake and Jackson Lake also indicates that the most recent event was quite old. And I've been in these, in some of these more smaller antithetic or places where the fault has splayed into multiple traces, where the total amount of offset is actually not that great, and they can trench through it. The depth to the offset horizon is quite thick. It's quite a far depth, which they would interpret as being kind of an old age. But they're holding, for whatever reason, even with myself, who's actively collaborating with them, they're holding their cards pretty close to them as far as what the age of the MRE is, the most recent event, which I can only interpret as them not converging on not having a consensus as to what they're seeing. If they all, I think, were on the same page, they would be a little more forthcoming about what their data is telling them. Anyways, this is all happening in real time, so it's kind of exciting. But this is what's published. This is what we're going off of right now, is that we have a fault trench that's showing evidence for at least one, perhaps two of the more recent events. These fault trenches, of course, you're limited by how deep you can dig across the fault, and so you're really only going to capture the most recent event, or maybe the most recent two, or maybe three events. But you're certainly not going to get the entire paleoseismic record from a fault trench. But this is important for the work that we're doing using the lake sediments. What's also important is that the magnitude of displacement and the inferred length of the rupture along the fault suggests that these earthquakes were huge, so magnitude 7 and greater, which of course pose very real threats to our community here. This is something I spoke on yesterday. Based on that scant data from the one fault, it suggests that if the most recent event was 5.5 or 8,000 years ago, that all of the other events occurred prior to that time, and so all of the other displacement that accounts for the total displacement at the site, so you have the 4 meters from those 1 or 2 earthquakes, but the total displacement at that site is 15 meters, so that means that the rest of that must have happened prior to 5,500 years ago at the least. And so it happened, it hasn't been an equal amount of displacement since deglaciation. There seems to have been periods of clustering of earthquakes and then maybe a period of quiescence or of no earthquakes. So this is a modeling study that suggests that the interaction of this ice mass that covered Yellowstone and the Tetons influenced the normal faulting that occurred after the ice mass was melted away. And so they are suggesting that indeed the unloading of the crust at the end of the last ice age caused an uptick in the amount of normal faulting. And thus most of the displacement we see displacing these glacier features may have occurred early on following deglaciation. And so this is an interesting, an interesting case where we see these deep earth processes interacting with more surface processes, climate-driven processes that are responsible for the timing of glaciations and the mass of ice on the crust. Yes?
When you said that the retreat of the glaciers caused an uptick in the normal faulting, do you mean that there was a rebound or that it went down further?
Yeah, and this is something that we were discussing yesterday. So we have a normal fault here, which is shown by this cartoon, and we have, in this case, the mountains are on the left side of this fault here. They're on the footwall. They're rising up relative to the hanging wall, which is the valley. During a fault rupture, you have both subsidence, and again, this is a normal fault, so there's extension effectively pulling these two blocks apart. But of course, the mountains are rising, and the valley is sinking, like that image, the profile image I showed you, where they mapped the depth of the valley. And so, what this modeling study is suggesting is that you have the ice mass of the Yellowstone ice cap and the mountain glaciers of the Tetons melting away caused an uplift of the mountains, but there must be some sort of concurrent subsidence of the valley happening as well. So it's unclear what the relative proportion of subsidence relative to uplift is or was.
There's a lot of studies of that, though, and we know that valleys go down a lot more than the mountains go up.
I was going to say that the sediment's got to be more compressible than the igneous
Well,
rocks.
it's not that. It's really the mechanics of the
extension.
And I've heard different numbers, everything from 3 or 4 to 1. That Ken Pierce was citing almost 8 or 9 or 10 to 1 last week.
Okay.
That's his opinion.
Yeah. Okay.
Well, and the other thing I learned on that trip, which is just a small thing, but it's visual, is he said that glaciation rounds things off and weathering makes the spires. So
Okay.
you can kind of look and see that the glaciers didn't make those pointy things, because that's not what glaciers do,
Mm-hmm.
which I thought was a really interesting way to look at it.
They made them, they just weren't on top of them. You got to think about the cirques cutting back
Right.
to make those spires, but no, there was not ice on top of the spires.
Mm-hmm.
It wasn't rounded off, like he's going from
Exactly.
Butte and like all of these other things around here, it rounds, it grinds them down.
Right.
Okay, so speaking of these glacial features, we're all probably familiar with this series of these iconic U-shaped valleys that transect the range here. Many of these valleys contain lakes that formed after deglaciation at the end of the last ice age, and then the sediment that's been accumulating in these lakes ever since then contains this continuous record of all things that are happening in the environment of the Tetons. And so lakes are out there on the landscape, and they're collecting everything from wind-blown dust and sediments to algae that's growing in the water column itself, or maybe plant material growing along the landscape around it, or sediments contained in the upstream catchment. And so lakes are great sediment archive that we can use for a variety of purposes. And that's exactly what we're targeting here. So to get back to this, the purpose of this project here is we're targeting sediments in these lakes to determine climate fluctuations in the form of glacier variations, including the timing and character of deglaciation of the mountain range, and then also the timing and frequency of major ground shaking events. So we'll start with some of these data here related to the timing of deglaciation. And this goes back to my graduate school days where I read this paper that Joe Licciardi and Ken Pierce were involved with that tried to summarize the timing of deglaciation in all of the mountain ranges in the western US. And they're comparing that here to water isotope data from Antarctica and Greenland, which you don't really have to pay too much attention to. But what I wanted to highlight is all of these different colors correspond to a different mountain range. And this orange circle is the Teton Range. And what they're showing is beginning 24,000 years ago to 10,000 years ago, they're showing that most of these glaciers were at their maximum position. So this is normalized glacier length, where 1 is 100% of the glacier was there. And then as we're going to present here, beginning around 15,000 years ago, we see all of these glaciers decreasing in size until they disappear to 0. And most of these glaciers begin to retreat early on, but what really got me interested and perhaps spurred this entire project is these 2 dots down here of Teton Valley glaciers persisting at their maximum positions well beyond or much more recent than all of the other valley glaciers that we have evidence for in the western US. And so what is going on there? This is thousands of years of time when the glaciers in the Tetons were still way down valley at their maximum position, when all of the other glaciers in the region, in the Wind Rivers, in the Front Range of Colorado, in the Pacific Northwest, are beginning to retreat. And so I started thinking, what could be causing that? And if there is a way to maybe tackle this problem from a different angle. Many of these data were produced through exposure ages of boulders or bedrock in these glaciated regions, or glacier deposits themselves, which is, at least at this time, was still a method that was being developed and refined. So the evidence from those 2 dots in that paper for the Teton Range really came from this earlier work by Joe Licciardi and Ken Pierce, where they sampled boulders and bedrock on the moraines surrounding Jenny Lake. And so this is another aerial view here of Jenny Lake at the mouth of Cascade Canyon, showing their sample locations where they had sampled boulders on the moraine crest. If I zoomed in here, we were talking about how these moraines are composite features. You can certainly see that around Jenny Lake, and they dated what they interpreted as a distal moraine and then an inner moraine surrounding the lake, and that gives them 2 different ages here for the age of those features, showing that the older moraine is quite a bit older, almost 1,000 years older than the inner moraine. And so this really kind of caught my attention. These are relatively young ages, right, compared to all of the other terminal moraines that have been dated in the western US. I thought this was interesting. So this was their 2008 paper. In 2018, this again is this 1835 USGS paper that Ken piloted. This is now showing their most recent state-of-the-art kind of image of their data set, this exposure age data set for now that Jenny Lake region, but also some of these other terminal moraine complexes across the range. And it still holds up that these are relatively young ages. So that's an interesting story here. And this is fun to look at because there does seem to be some differences in the timing of deglaciation along the range, and whether that is real, and whether, if so, if that's driven by changes in the morphometry of the valleys, or maybe in the accumulation rates at the heads of the cirques, is something that I believe they're beginning to put together into some sort of publication. So I just wanted to demonstrate that this information is being accumulated, and at least in this paper is published, but they've expanded that data set quite a bit. I showed this yesterday. I just wanted to show this again because I think it's helpful in visualizing what's happening here. So we're looking at a profile of, say, Cascade Canyon or any canyon where a glacier was occupying the canyon, or the mountain range here, from its cirque all the way down to its moraine, and the peaks were, again, sticking up above these glaciers here. And then at the end of the last ice age, so these moraines are being constantly constructed at the snout of the glacier. Once the glacier begins to retreat, the moraines are left there, they're abandoned. And if the glacier retreats across these basins they excavated, a lake will form there. And these lakes are oftentimes dammed by the moraine features themselves. And so the glaciers will continue to retreat in the face of warming climate at the end of the Pleistocene, and leaves lake basins at the base of the range, but also in places up in the cirques and along the way. And these lakes, again, are just accumulating sediments since that time period.
And how thick would that glacier have been at any, average or in a particular place?
A few hundreds of meters. So they're not that thick. You can see evidence for that in the valleys themselves. If you go out to these regions, you can actually see it in the LiDAR imagery pretty well. You'll oftentimes see a change in inflection where it's steeper where in the place where the glacier was occupying, and then begins to get a little bit less steep above that. And so you can visualize how thick these glaciers were, which were on the order of 500 meters thick, something like that. They're not that thick.
But still well over 1,000 feet thick.
Yes.
Yeah. Which is a lot in Cascade Canyon.
Right, but nowhere near the actual.
Yeah.
I thought I had a picture of it.
Not the height of the range,
Yeah,
of course.
not the actual height of the valleys are so deep. You can see it actually kind of well here. So this, and you'll have to maybe come up and look at it, but that is showing you the trim line of the glacier, this change in slope that demonstrates how high the glacier
Kind of going
was in the
from
valley.
V to U.
Yeah. Okay. So we set out to target these lake sediments, and we did that through geophysics, which is just mapping the lakes using various geophysical tools, including seismic stratigraphy, so acoustic sub-bottom profilers, where we can map the thickness of the sub-bottom of the lake, of the sediments in the lake. And then we also drove out this essentially marine vessel from the University of Minnesota Duluth. They brought out one of their Lake Superior boats to collect multi-beam sonar bathymetry of Jenny Lake. So we mapped the topography of the lake bottom at really high resolution, and then also the stratigraphy of the sediments in the lake. And then, of course, we also collected cores, and this is some of the most exciting, some of the most fun type of fieldwork, because it involves coming out here in various seasons, including in the springtime. And I'm a huge skier. I love to ski, so this allows me to actually do fieldwork with ski boots on, which is pretty unique for me. So here we are out on Jenny Lake, collecting cores. We record some of these higher cirque lakes, both in the summer and in the winter conditions. So this is us accessing Surprise Lake up at the head of Cascade Canyon, where we camped up there. This is coring Delta Lake in the summertime from a small pontoon system. So in cases where we're coring in the winter, we can really spread out on the ice, not worry about getting wet, obviously, or falling in. And you don't have to worry about dropping tools in the ice. When you're coring in the summertime, this is a pretty remote lake, and so we're limited by what we can carry. And these are two really small pack rafts that pack down into kind of a small pillow-sized craft, and it really doesn't have that much buoyancy in it. So and you have to keep all of these tools, which you can see kind of distributed here, within the boat and not drop them, as well as anchor the boat and everything like that. So I much prefer working in the spring. However, the conditions are much less reliable. So we really have to hit the timing perfectly, because if it's powder snow, if it's still actively snowing, we can't really work, because then we're trudging around in powder snow and everything's freezing if it's below freezing. But then once these lakes begin to melt, then you start to punch through the various layers of kind of refrozen snow and ice on the lake surface. And so there's this sweet spot and trying to time that from another location, California, for example, to try and book travel and arrangements and everything and get the whole team here to core, hoping for that weather window is oftentimes stressful. Here's us coring on Jenny Lake. Here's us coring on Phelps Lake this past March. Both of these systems in these deep lakes require the deployment of a long tube on cables down to the bottom of the lake. And so we'll auger a hole through the lake ice and lower a long tube down to the bottom, and then hammer that tube through the mud, basically just by attaching a heavy weight to the top of it that's attached to ropes or cables that go up to the top of the tripod, and then pulling down and letting go multiple times, thousands of times, and hammering that tube down into the mud.
How do you find the hole for the second core?
Yeah, so in places like here in Phelps Lake, as I'm going to show you, there's over 15 meters of mud that has collected since deglaciation. And of course, we're not going down with a 15-meter tube because that's kind of unrealistic to bring up to the surface and work with. So we're going down in 2-meter sections. And so we have to find that we're going down in successive 2-meter sections, so we reoccupy the same hole each time, which is another reason why working from the lake ice is preferable, because we don't have to worry about anchoring on the water and the wind shifting us around. This is a pretty interesting kind of custom-built core rig that I have that has, and I don't have a good picture of it, I don't think, but it's first of all stably located over the hole by this tripod, and then it has a couple features that allow it to reoccupy the same hole. One of them is this mechanical wing or arm that you can deploy, and so it's like a big wind vane type of thing that prevents the core from spiraling as you're lowering it. And so it just as you're lowering it, instead of it rotating around, which it would tend to do without that feature, it just goes straight down. And believe it or not, you can lower it even through, in Phelps Lake and Lee Lake, upwards of 80 meters of water column. You can lower it right down into the same 4-inch diameter hole that you had been coring in with the previous drive. It's pretty remarkable.
So you don't have any sort of docking umbrella?
Like a funnel or something that they use in the marine realm. No, we don't use one of those. And it doesn't actually have a problem. We also have a way of locking a piston at the nose of the core. So even if we're off by a little bit, we can lock a piston at the nose of the core and tap it down to the depth that we ended the last drive at without actually filling the barrel with any mud at all. We're just kind of pushing it out of the way, and then release the flanges and lock the piston, and then begin coring and filling the barrel at that desired depth. So even if we miss the hole, we can still capture that interval of sediment that we were hoping to get. It's a really neat system.
How long does it take to drive 2 meters?
It depends.
If you don't hit a rock.
If you don't hit a rock. About an hour.
Not bad.
Not bad. So we've done that at all of these large lakes along the range front, and then some of these alpine lakes in different regions. I'm going to highlight some paleoclimate data from Jenny Lake, and then also some paleoseismic data from the lake also. So this is Jenny Lake here. This is the multi-beam bathymetry. So believe it or not, this is quite high resolution bathymetry or topographic elevations of the lake surface. So this is mapping the lake surface here, and the colors represent water depth, with the deepest part of the lake about 75 meters deep right in front of the valley mouth, and it gets shallower around the perimeter. You can follow the fault trace through the lake and also see some of these interesting features which we discussed yesterday related to landslides that happened on the slope above the lake that ran out into the lake itself and are expressed as these block and fan deposits. So I'm just going to throw some lines on top of that image, highlighting in blue these 2 landslides that happened. In white, those are the core locations that we've visited, and then these lines here are the positions of the seismic profiles that we've taken of the lake sediment fill. Here's 2 examples of the seismic profiles. The top panel is right across the northern portion of the lake from the valley mouth eastward to the moraines, and then the bottom is a north-south transect, showing, in each case, the conformable sediment that's accumulated since deglaciation, as well as some other really interesting features like the fault itself offsetting that lake sediment, and these landslide deposits. So really, really neat lake for many reasons. We can date these sediments using a combination of radiocarbon dating on organic material, and then also the positions of these 2 well-known volcanic eruptions that happened during the past 15,000 years, one being the Glacier Peak ash from the Glacier Peak volcano in Washington, and the other being the Mount Mazama tephra from the eruption that formed Crater Lake National Park. And then we can also do some annual layer counting in the lower portions of the sediments where we have glacial varves, which allow us to count, much like a tree ring, annual accumulations of sediment back through time, all the way to the base of the sediment film.
And your numbers alongside are centimeters?
These are centimeters, yep. These are just 3 examples of 15 or 20 centimeter thick portions or intervals of the cores from different lakes, showing how these volcanic tephra layers are expressed, how we see macrofossils. This is a small piece of a fir cone that we dated, and then are these glacial varves.
So that's not one continuous core.
Nope, this is from, I think, Taggart Lake here, Jenny Lake, and this is Phelps Lake. These are just different examples of the type of sediment we're pulling up. This is just showing on the bottom, this is showing the major element chemistry of the Mount Mazama and Glacier Peak ash deposits. And this is how we attribute a volcanic ash layer to a known eruption, is we measure the major element chemistry of the sample of the unknown and compare that to a repository or a database where people have gone through to tephra layers around the world and measured this chemistry. And so then you compare your unknown sample to the known database of tephra chemistry. And this is how we assign them to these different eruptions. And then we support those correlations with independent age constraints from radiocarbon. So here I compiled a few physical parameters of the lake sediment in Jenny Lake for the last roughly 14,000 years to present here, showing all sorts of parameters such as the flux of clastic or minerogenic material to the lake, which of course was high when there was glaciers occupying the catchment, and then gets lower through time, as well as accumulation rates and things like that. I'm just demonstrating that indeed we can pull out all sorts of information from these sediments, which we can use for various purposes. What I've highlighted in blue here relates to the timing or the age of the basal sediments. So the most basal sediments here correspond to the timing of deglaciation, which I thought coming into this I would be able to collect and then compare to those exposure ages collected using independent techniques on the moraines themselves. It turns out collecting these basal sediments is quite difficult because you're coring through glacial sediments and then often down into glacial till. And there's very little to date. There's very little organic material in that portion of the core because I don't think these moraines and the region around the lakes were actually vegetated at that time. Or if so, there wasn't as much vegetation growing around the lake or in the catchment as there is today. And so there's very little to date, and you're reliant upon your most recent chronologic constraint, whether it's the Glacier Peak ash or a radiocarbon sample up here, and then trying to count down through these varves, which can be quite difficult. So here's an example of it doesn't show up too well actually in this, of the basal sediments that we capture in Jenny Lake, where this is upwards in that direction and we're getting older and older through time, and this is what we bottomed out on. And this is some type of glacial diamict that includes these coarse pebble and cobble deposits. So this could be till, or it could be diamict streaming out from the snout of the glacier before it had fully exited the lake. And so we know we're in the time of deglaciation, right around that window, but to be able to say definitively whether what the age of this feature is and what it exactly corresponds to is a little bit challenging, but I think it's within the uncertainty of the exposure age method. And so we are able to count down from our nearest control point using the VARV stratigraphy. You can see things get a little disturbed and wonky down through here, and we get an age of around 13.9 to 14.1 thousand years ago for the timing of deglaciation of Jenny Lake, which actually corresponds quite well to the innermost moraine crest of that was published by the exposure age data. Questions on that?
Do those varves change size as you go through the...
They absolutely do. Yeah. So they they're thickest in the bottommost portion of the core when the glacier was biggest and closer to the lake, and then they get thinner and thinner and thinner through time as the glacier retreats up valley until you get into these sediments that don't seem annually laminated. Perhaps when there was just small cirque glaciers in the canyon, but not generating enough fine material to really create these seasonal differences in deposition, which compose a varve, an annual couplet.
Okay, well, so most of these are from the cirque glaciers, not from Pinedale itself.
This sediment was deposited by the Pinedale Glacier in its phase of retreat, beginning 14,000 years ago.
But then a lot of it was coming off the mountain from the parallel glacier.
In the case of Cascade Canyon, there aren't too many tributary valleys, except for the three main forks at towards the head of the valley of Cascade Canyon. So there aren't many tributaries along the way leading up to the forks. So it's unlikely that those regions harbored very much ice, if I'm understanding your question correctly.
I think she's separating the Alpine Valley glaciers versus the large ice sheet that came out of Yellowstone.
So Jenny Lake was actually shielded from meltwater coming from the southern margin of the ice cap, the Yellowstone ice cap, and that it seems that meltwater was not rooted into Jenny Lake, but rather around the encircling moraine complex, and then circled around it, and then kind of caught up with what is now, I guess, Cottonwood Creek to the south, and flowing south from there.
And the Alpine glaciers
Would have been coming from the hanging valleys.
Alpine glaciers are Pinedale too.
Okay, that was my confusion. Yeah, so these Alpine glaciers, we also are calling them Pinedale Age because they were formed during the Pinedale glacial interval, but they're separate or distinct from the Yellowstone ice cap. And Jenny Lake would have been receiving meltwater from the glacier in Cascade Canyon, but also from really the String Lake flowage, which is getting meltwater from Lee Lake, which was partially overridden by the ice cap. So now that you're actually saying this, I'm wondering if these very early times would not have been also receiving meltwater from the ice cap. That's interesting.
And I have another question. You sort of implied earlier that when the Pinedale came through as far as it did, that it scoured all of the deposition from Bull Lake. Did you mean to say that? Or did I misunderstand?
I'm sorry, I missed that question.
So you have Bull Lake deposits, and here comes the Pinedale.
100,000 years later.
Right. However, I wanted to be clear about what you were saying about that basically it took off all of the Bull Lake. That's not true, correct?
No doubt the valleys in the Tetons would have been occupied by ice during the Bull Lake, or it's most likely. We just don't have evidence for that because it's thought that those valley glaciers were basically just tributaries to the ice sheet itself, which advanced right through the valley. And so those valley glaciers wouldn't have formed these moraine features that they formed during the Pinedale.
No, but I meant the scouring of the second glacial time would have scoured not down to the bedrock, you would have left some of the Bull Lake.
They would have been scouring into sediments deposited in the basin, in the Teton, the Jackson Hole Basin, left by the retreat of the Bull Lake ice, during the phase of retreat of Bull Lake ice.
So that's still there somewhere.
It's still there. The valley itself is very much an outwash-dominated basin, and we see evidence for that most recently. If you look at that LiDAR data set, you see all of these channels covering the entire valley floor, all of these outwash channels from the ice cap. Not as much evidence to the north for Bull Lake advances, but it would have no doubt been there. It's just been, I guess, buried by Pinedale outwash. These are great questions, though. And again, I would refer you to that manuscript by Ken and others who have really looked at these outwash channels, these paleo
About a
channels.
third of it. So.
Yeah, it's a beast of a paper.
Yeah. I didn't-
Okay, I'm going to also present some evidence for Holocene glacier fluctuations of the extant cirque glaciers that do exist in portions of the range. Like here's the Teton Glacier at the head of Glacier Gulch. Many of these glaciers that exist are sort of artificially fed by redistributed or wind-blown snow or snow that's avalanching off of these steep slopes above them, like from the Grand Teton and Mount Owen and things like that. So you have increased accumulation rates in these high elevation cirques. And so we core, like I mentioned before, we core Delta Lake to recover these sediments that are preserved there outside of the limit of the late Holocene advance of the Teton Glacier. This was a challenge, getting up there and collecting these cores in summertime. We've since gone back in the spring when we could core from the ice surface and collected a really nice record that is quite likely varved for portions of it, demonstrating that the Teton Glacier has been in existence for at least the last 12,000 years, which is contrary to what we originally thought, that it reformed in the late Holocene and is about to disappear. So studies of the mass balance of the glacier indicate that it's likely the glacier will disappear in the coming centuries, and yet we're able to demonstrate unequivocally that the glacier has been there for much of the Holocene.
So did it not melt at deglaciation? In other words, has it been there since? You're saying deglaciation is 14,000 years ago at the bottom, at the valley bottom.
Yep.
Do these things persist right through?
That's unclear.
You're pretty close.
Didn't actually make it to the basal till, or to that age, that time period. This is another example where I grossly underestimated the amount of sediment contained in these lakes, and we collected an 11.5 meter long core from Delta Lake. That was, I thought, being over conservative with how much sediment I could possibly dream of there being in Delta Lake, but we didn't bring enough extensions for the core, and so we only got basically 12 meters of mud, which wasn't enough to get to the bottom of the profile. So we get back 12,000 years, but as Mike's saying, there's this really interesting time period between 12 and 14,000 years ago where we could try and determine whether or not the glacier is actually just a remnant of the Pleistocene glacier that occupied the canyon, or disappeared completely in the face of the warming that caused these glaciers to melt, all the other glaciers in the range to melt away. So we have to go back, which is easier said than done. This was very challenging. At 12 meters of mud, and using a system like this is we're maxing out kind of the system, these lightweight coring systems. Yeah.
So can you look at those varves and see shifts in climate, like changes in precipitation in the area?
Absolutely. And so I have a student right now who's creating thin sections of these cores to really measure the thickness of annual sedimentation carefully through time and relate that to some sort of function of the glacial meltwater hydrologic system, which can be related to the amount of accumulation or the amount of melt that happens each year, which is basically the strength of the glacial plumbing system. And that's all recorded by the amount of sediment produced by the glacier each year, as well as the actual size of the glacier, which is kind of the first order control on the amount of erosion. So this is interesting for many reasons.
And would you extrapolate to the other remaining Teton glaciers, like Falling Ice or Skillet, that they're also in the same ballpark of 12,000 years old? Can you do that?
I would not feel comfortable doing that for a few reasons. One, there's very little morainal evidence for other glaciers, cirque glaciers in the range, because they're so steep. Like the Falling Ice Glacier and Skillet Glacier don't have these big moraine systems, and perhaps it's a good question. It could be. All of these glaciers are here almost artificially because of their unique position in the range, which suggests that it's not just temperature that's controlling their mass balance, but also the amount of precipitation that's falling through direct snowfall, but also being redistributed over ridge lines by prevailing winds and things like that. So there's some interesting kind of complications to understanding what's controlling glacier fluctuations during the late Holocene.
So my understanding is from the talk we had at the weekend, is that the prevailing climate, prevailing winds and precipitation are from the south and southwest, and then as it hits those ridges, most of it is dumped on the western side. So the accumulation on our side that include Yellowstone in terms of where that dump is? It's always more or less, because there aren't mountains up there like this.
They're not mountains up there like this,
In Yellowstone.
but they're highlands, and as is
It create that dump.
demonstrated,
It
there's
creates a
huge
barrier.
snowfall. Right, there's Yellowstone receives much more snow than we get here because of those highlands and because of these storm tracks being funneled up the relative lowlands along the pathway of the Yellowstone
Well,
hotspot.
that's what I was concerned about, because as I understand it, it's coming mostly from the west, and the snow gets dumped on the west, not on the
Right,
east.
right, and that's why here, this glacier here is likely, since we had these prevailing westerlies, there's winds blowing or redistributing snow that fell on maybe the western slopes over the ridge line, and then it accumulates in the lee of this Gunsight
You're
Notch
also
in this high
saying there's
ridge.
some sort of prevailing weather that comes up valley,
Up valley.
up the big valley.
Snake River Plains.
Okay.
Right, I think what Elizabeth, I think to answer your question, what Darren is saying is that these slopes that are on the east side are getting all this wind deposit. I mean, when they talk about avalanche hazard, wind deposited snow is much greater than what actually falls. And so these areas that are just on the other side of where the wind is coming from, you can imagine the wind coming up Teton Canyon on the west side, it crosses the crest and it just drops all this snow. And that's what's happening like in Paintbrush Divide, and that's what's happening in these high
But
little,
my
little
understanding is that
cols,
it does that, but it does, most of the drop is on the others, is on the west side.
Right, but these are very small local areas.
Mike's not talking about the precipitation, he's talking about the wind loads.
Right, and I'm talking about small areas that are like an acre in size or a few acres, not square miles.
Wind blown snow, but we're talking about the bulk of the weather and the snow.
We need to
Right,
move
yes,
along. It's already 2 o'clock. I don't know how many more slides you got, but
I'll
at some
talk
point
to you
they're gonna
later.
get upset about us sitting here with dishes.
Okay.
Why don't we take a break and take the dishes out?
If you'd like. So then I was going to talk on what I guess many of us have heard last night was this second component of the project is to focus not on extracting climate and glacier records from these sediments, but that of related to strong ground shaking and earthquakes.
It may be that we should take the dishes.
Would we like it?
Take the dishes.
Just because
And
they
we'll take yours,
they don't
so
wanna-
you can just chill for a minute.
Okay.
they don't want to keep the kitchen open for
That's
indefinitely. So let's get rid of that real quick.
Not making-
And then I think we'll get it.
This is a great talk. It's inviting so many more questions. You're gonna have to just come back.
Mike, I have a question for you, because you said those different ones, the skillet and whatever, are they at
They're on
the
Mount
same?
Ram.
Are they all at the same elevation?
Yeah, they're all hot.
So it
Yeah.
could possibly be, it seems
Oh,
like.
it's what
I mean, it
Darren is
seems
saying.
rational.
These are these little alcoves almost that are catching all this precipitation. And they're catching it because of where they're situated.
Yeah.
And what Elizabeth is saying, she's sort of confusing a couple of different pieces there. So can I take these glasses?
No, these are Joe's, and they don't mind you leaving
Oh, they don't.
glasses
Yeah,
in
and
here.
that just goes on with the dishes, we'll see with the others. Well, thank you very much.
You're welcome.
He's gonna finish some more.
Just put those on the counter
How much longer do you think you have?
As long as you guys want, I can wrap up really at any time.
Okay.
I just didn't want the kitchen to get mad at us.
Yep.
That's all my crap over there.
So it seems like some of those little glaciers up there, I know in the Sierra, there are often, those little glaciers are on the east-facing, north-facing slope, so there's less sun and heat on them, so they don't melt.
Yeah.
It's not just other,
Right, no doubt. The Teton
So-
Glacier is shaded almost all day long.
yeah, they're
for most
shaded,
of the
like the
year.
Dana Glacier and some of those, so. And as far as snow accumulation, but there's also the lack of melting. I think.
Right.
I think we're good to go now.
Okay. Okay, so I wanted to go through
Mike.
this because indeed not all of us were here yesterday, and I think this is quite exciting. The idea here is that past earthquakes that occurred generating this large displacement along the range front would have also triggered slope failures on unstable slopes. And those can be in the form of landslides, like I showed you some evidence for, but also within the lakes themselves as slope failures of either the inflow deltas or along the perimeter of the lake on the back slopes of these impounding moraines. And so to test this idea that indeed earthquakes were triggering slope failures and that we can use these slope failures to reconstruct the timing and frequency of past earthquakes, we set out to core along the broad section of the fault, to core lakes along the fault itself. So I'm going to show you some data from Jenny Lake, but then also brand new data from Phelps Lake that we just collected this past year in the southern region of the park itself. So the idea is that we set out to core in multiple locations within the lake. That's these white dots here. And the goal was to core near the fault through a series of what we will interpret as slope failure deposits that accumulated in various regions of the lake that were either generated by slope failures on land as landslides or slope failures of the inflow delta, which in many cases in the Tetons is sitting right along the fault itself. So this type of study has been done in other regions, tectonically active regions. This is an image of the seismic stratigraphy in Lake Tahoe, showing a series of these earthquake deposits in that lake that they set out to core through and generate a paleoseismic record from that sediment archive. So we're doing much the same thing here. This technique has been applied in other regions around, but it is fairly recent. This in the Tahoe was only published in 2013. So here's a section of core from Jenny Lake that's on its side here, showing depth below lake floor on the x-axis, and showing some interesting features such as the Mount Mazama tephra layer, which shows up as kind of this bright white layer here, and then below that two disturbance events, one here and then another one here, that are expressed in a similar manner. In this case, these two are not a similar thickness, but they have the same expression of coarse sand, depending on the event. Sometimes it's coarser or less coarse than others, but it's always a sand-rich deposit that grades normally upwards to a silt and clay cap. So fining upwards, and they often have this very sharp erosional basal contact, very indicative of a turbidite flow. These show up nicely in physical parameters of a sediment, whether it's density or grain size itself. And so this is just for the same section here, showing how we see an increase in density through these turbidite features. And so when we make these measurements for the entire, in this case, 6.5 meter long core, we see that there's a series of these events that happen, but it's not uniformly distributed through the entire core itself. We see periods where there's more prevalent disturbance events, and then periods where there's not as many events. So this is on depth here, looking at density. We could also look at sand concentration for these same two sister cores, showing how we see all of these disturbance deposits are sort of clustered towards this center portion of the core. This can be misleading though, because we're evaluating changes through depth in the core, and so then we use those chronologic techniques to convert depth to age, and that's of course more meaningful for us. So that's what I've done here, is I've just applied our age scale or age model based on the age of all these black triangles here, where we're looking at changes in density through time. And so this is the bottom of the core, 14,000 years ago to present, showing a series of these turbidite events that are all clustered in the first half, or the first 6,000 years, and which we can place ages on here based on the radiocarbon or tephra age of the sediments directly above and below the event deposit. So this is what I showed yesterday, showing these 8 event deposits, which we have captured not only in Jenny Lake, but now we're starting to observe in these other lakes that we're coring. And so what's important really is that we can demonstrate that these turbidite deposits, these disturbance events, are indeed related to earthquakes. And one way we can do that is to generate a record from multiple lakes along the fault and demonstrate that the timing of these events all line up, but also being able to correlate them to other features which are associated with past surface ruptures. Importantly, the most recent event that is documented in that Granite Creek Trench, which they date to around 7.9 or 8,000 years ago, which we see as being similar to the age of the most recent large event in the lake sediments. So that's why whether or not that was one event or two events in the Granite Creek Trench that they observed is really important, because that has large implications for our study. But we not only see that most recent event, but a whole series of events that took place prior to that, some of which line up with the independently derived ages of these landslides at 8.3 and 13.9 thousand years ago, which we dated using exposure ages on boulders in the landslide path and bedrock on land. And these ages line up with the ages we derived from the sediment cores, indicating that indeed these events, these slope failure events that we see in the cores are related to the landslides themselves. Of course, you could make the argument that landslides happen without a seismic trigger, but in this setting, I would argue that it's more likely that a landslide would occur in response to a strong earthquake than as a stochastic event. But of course, they do happen that way, so you can't say definitively. What I wanted to summarize here is that these lake sediments are promising archives of climate, glacier, and tectonic history of the Grand Teton National Park and the Teton Range, and I think they're very promising in helping us to tease out or reconstruct the history of, in this case, large earthquakes or tectonic activity in the range front, and that presents a new way of evaluating the seismic hazard or to aid in resource management efforts. And so this study is very much ongoing, and we're trying to replicate what we're demonstrating in Jenny Lake in other lakes. And so here's some data that I just plotted this morning before coming down here. That's hot off the press. I just had my student send me this data. She's been measuring the grain sizes in the sediment from this core we just collected from Phelps Lake back in April, showing how indeed in these turbidite events, which we notice in Phelps Lake, we see the same expression, and that the age of these features line up. Well, we haven't actually gotten our radiocarbon ages. We haven't even submitted them yet, but we expect to have them by the end of this year. But just visually, the Mount Mazama tephra layer, which we know the age of, is right here, and we certainly don't need to date that. So this most recent large event we see in Phelps Lake corresponds to the most recent large event we see in Jenny Lake, which is located 40 or 50 kilometers away, apart from each other. So it's this is really compelling.
So you do have that one date for
we
sure.
We have the Mount Mazama tephra layer right here, and we see this, and it's expressed in the same manner. Directly below the tephra layer, we see this turbidite deposit. It looks the same. It's coarse sand finding up to a silt and clay cap, and it's the most recent large event. So it's.
And what are the two lakes again?
This is Phelps Lake
And what are you comparing it to?
to the Jenny Lake data set. So it's pretty interesting. So perhaps the next time I get to show you guys this data, we'll have ages for this, and we'll be able for this lake and the Lee Lake core. So we're really kind of making ground on generating these records from these large lakes. It's a process, though, as you can imagine, collecting these 15-meter long cores, and particularly working at a liberal arts school where I don't have a team of graduate students or postdocs. Producing this data in a timely fashion requires quite a bit of effort. And luckily, Occidental College has great students, really motivated students who are willing to kind of work for free in the name of science and their degree, I guess, in generating this data set. So yeah, with that, I guess I can end there and entertain any further questions or continued discussion offline, so to speak.
Thank you.
So I have a question. You had referenced last night Lake Solitude.
Yeah.
And we were going to touch on the age of Lake Solitude.
So we don't have, Lake Solitude is this lake here. That is when we went to core Lake Solitude.